Hello there. Hope you all are doing absolutely fine. My name is Pranav Durai and I am a computer vision engineer at OpenCV. I'm also a research fellow at Stanford University School of Medicine, Palo Alto. I'm a passionate quantum AI researcher as well. I'm currently looking into accelerating AI using quantum machines. It gives me immense pleasure to be able to deliver this keynote on Quantum Linux, pioneering the future of computing. I wasn't able to physically make it to Monterey to meet you all in person, so this will be a virtual presentation. Alright, so let's dive in. Ladies and gentlemen, let's embark on a journey into the fascinating world of quantum computing. Here you see a portrait of the brilliant physicist Dr. Richard Feynman, whose pioneering work laid the foundation for quantum computing. In his landmark paper, Simulating Physics with Computers, Dr. Feynman proposed the idea that we could use computers to simulate the behavior of quantum systems. This paper actually marked the birth of quantum computing, where classical computers reach their limits and quantum computers take the center stage. Now just have a look at the illustration of a quantum computer. Unlike classical computers, quantum computers harness the extraordinary properties of quantum mechanics, such as superposition and entanglement, to perform computations that were once considered impossible. This is just the beginning of our exploration. As we dive deeper into the quantum computing universe, it's crucial to understand the fundamental difference between classical and quantum computers. Here, you're witnessing a brief video that exemplifies this contrast. In classical computing, like what you see here, we rely solely on binary bits. These bits can either be in the state of 0 or 1, like light switches that can be turned off or on. Classical computers process information by performing logical operations on these binary bits, creating the foundation of our digital world. But when we transition into quantum mechanics, the rules of the game change drastically. We now have qubits, unlike classical bits. Qubits can exist in the state of 0, 1, or both 0 and 1 simultaneously. This is crazy, right? And this phenomenon is known as the superposition principle of quantum mechanics. Superposition allows quantum computers to process vast amounts of information in parallel. It's a fundamental property that forms the backbone of quantum computing's power and potential. When we talk about computing, whether classical or quantum, gates are the fundamental components. On the left, you see a collection of classical gates, and on the right, an array of quantum gates. Let's dive deep into the intriguing differences between these gate sets. Here on the left are the classical gates. These gates, such as AND, OR, NOT, are the foundational building blocks of classical computing. They manipulate classical bits to perform logical operations. Now on the right, we have quantum gates. These gates are tailored for quantum bits or qubits. Quantum gates, like the famous Hadamard gate and the CNOT gate, harness the superposition and entanglement properties of qubits to perform quantum operations. These quantum gates enable us to perform remarkable tasks such as entangling qubits, superposing them, and executing quantum algorithms that classical gates can only dream of. Quantum computing's strength lies in the creativity and precision in which we employ these gates. In this slide, we are going to explore the practical side of quantum computing by comparing classical and quantum adder circuits. On the left, you see a classical 4-bit adder with a carry function circuit, and on the right, a quantum adder circuit. Let's dive deeper into the details. Here on the left, we have a classical 4-bit adder. The circuit is a workhorse of classical computing, performing addition and other arithmetic operations. The carry function circuit ensures that the addition is accurate. On the right, we have a quantum adder circuit, and this circuit is designed to perform addition on quantum bits or qubits. It uses quantum gates and the principles of superposition to explore multiple combinations of qubit states simultaneously. The power of the quantum adder circuit lies in its ability to leverage superposition and entanglement to perform complex calculations exponentially faster than classical adders. Quantum computing isn't just a faster version of classical computing, right? It's a different paradigm that opens the door to solving problems that were once beyond reach. Alright, so what are the current trends in 2023? IBM is set to introduce a cutting-edge quantum machine in 2024. This quantum behemoth of a machine will support a staggering 10,000 qubits, marking a significant leap in quantum computing power. What's even more astounding is that this quantum marvel is projected to be 34 times faster than IBM's previous quantum machine. This quantum leap in speed opens up new possibilities for solving complex problems that were once considered impossible. Now, IBM's commitment to advancing quantum computing is actually a testament to the rapidly evolving landscape of this technology. In Santa Barbara, Google's research lab is shaping the future of quantum computing. It has become a premier destination for leading physicists and engineers focused on superconducting qubit technology. From this location, they plan to build an error-corrected qubit and serve access to Google's quantum computers and support the discovery of new applications for the NISQ era of computing. With an impressive track record in quantum processor development, including Foxtail, Bristlecone, and Sycamore, Google is at the forefront of quantum technology. Ultimately, Google's mission is to make the world's best quantum computers accessible, enabling humankind to tackle previously impossible challenges and redefine the future of computing. The question now is, why does quantum computing even matter? The answer lies in the transformative potential across various domains. Let's explore 3 key areas where quantum computing shines: cryptography, optimization, and drug discovery. Quantum computing's impact on cryptography is actually profound. Classical encryption methods such as RSA rely on computational difficulty of factoring large numbers. Quantum computers possess Shor's algorithm, which can efficiently factor these numbers. This poses a significant challenge to classical cryptographic systems, as it's like discovering a master key to countless locks. The need for secure communication is important, and quantum-resistant cryptography is essential to safeguard sensitive information. Quantum computing forces us to rethink and innovate our cryptographic techniques to stay ahead in the race against potential adversaries. Optimization problems are ubiquitous in real-world scenarios, from supply chain management to financial portfolio optimization. Quantum computers offer a unique advantage in solving these complex problems. Drug discovery is a painstaking and time-consuming process. Quantum computing promises to accelerate this journey significantly. Quantum computers can simulate molecular interactions with unprecedented speed and accuracy, helping researchers identify potential drug candidates more efficiently. This is like having a microscope that not only reveals the structure of molecules, but also provides insights into their behavior, interactions, and potential therapeutic properties. Quantum computing holds the potential to bring life-saving medications to the market faster and with great precision. Alright, here's my proposal. Quantum Linux. And here's what I envision for the next big step of Linux and computing. Quantum resource management. Quantum Linux should perform resource management through its quantum-aware scheduler. It leverages insights from the quantum kernel and quantum hardware to dynamically allocate resources to quantum tasks. It ensures that qubits and quantum processors are optimally assigned to different tasks. For example, in a quantum program with multiple quantum circuits, it allocates qubits efficiently, minimizing contention and reducing the probability of errors. And this dynamic allocation is essential for optimizing quantum computations and improving their overall performance. Quantum algorithm optimization. Quantum Linux should include a suite of optimization tools tailored for quantum algorithms. And these tools aim to reduce gate count, minimize the depth of quantum circuits, and optimize gate ordering. Like skilled craftsmen refine their work to perfection, Quantum Linux should be able to refine quantum circuits to minimize errors and enhance efficiency. It needs to perform gate-level optimizations, including gate fusion and gate cancellation, to ensure that quantum computations are as accurate and fast as possible. Additionally, it should also support various quantum programming languages, making it accessible to a wide range of developers and researchers. Quantum hardware integration. Quantum Linux will seamlessly integrate with diverse quantum hardware platforms. Its quantum driver layer abstracts the hardware specifics, allowing quantum algorithms to be hardware agnostic. This integration is crucial as it ensures quantum programs can run on various quantum processors without the need for extensive modifications. Quantum Linux's hardware integration needs to promote compatibility and interoperability within the quantum ecosystem. Security and isolation. Security in quantum computing is a crucial aspect. Quantum Linux needs to address this through robust security measures, including cryptographic key management and quantum-safe protocols. It needs to isolate quantum processes from one another and from the host classical system. This isolation is essential to prevent quantum eavesdropping attacks and ensure the integrity of quantum computations. Quantum Linux also should implement secure boot processes and hardware-based security features to protect against unauthorized access or tampering. And this should operate mostly like a secure vault, safeguarding sensitive quantum data and probably cryptographic operations. And last but not the least, hybrid computing. Quantum Linux should embrace hybrid computing, where classical and quantum resources work in synergy. It needs to allow quantum tasks to be embedded within classical programs, enabling hybrid quantum classical algorithms. Quantum Linux also needs to provide a seamless interface between classical and quantum components, ensuring efficient data exchange and synchronization. Hybrid quantum classical algorithms can leverage the strengths of both classical and quantum computing, broadening the range of practical quantum applications. So how does the architecture look like? And how do we design such a complex system? Now let's look into that as well. At the bottom of Quantum Linux's internal architecture, we have the quantum hardware, which includes the physical quantum processors, qubits, and supporting infrastructure. These are the physical devices that perform quantum computations. Now, directly above the quantum hardware is the quantum kernel. The quantum kernel is the core of Quantum Linux, responsible for managing and controlling the quantum hardware. It handles tasks such as qubit allocation, gate execution, and quantum error correction. Adjacent to the quantum kernel is a classical machine, representing the host classical computer that runs Quantum Linux. This classical machine manages the overall execution of quantum programs, including scheduling, communication with quantum hardware, and interfacing with the quantum kernel. Above the classical machine is the quantum simulator, and this component is a crucial tool for testing and debugging quantum programs. It emulates the behavior of quantum hardware and is essential for algorithm development and validation before executing it on actual quantum processors. The drivers interface with the quantum hardware, providing low-level control and communication. And they are responsible for translating high-level quantum operations into commands that the quantum hardware can execute. The compiler is responsible for translating quantum algorithms, often expressed in high-level quantum programming languages, into executable instructions for the quantum kernel. It optimizes quantum circuits, reordering gates and reducing gate count to enhance the efficiency of quantum computations. Quantum Linux should include a set of quantum libraries that provide pre-built quantum functions and algorithms. And these libraries save time and effort for developers and researchers, enabling the reuse of common quantum components and algorithms. At the very top of the architecture, we have quantum applications. Now, these are the end-user programs and tools that leverage Quantum Linux to perform specific quantum tasks such as chemistry simulations or cryptography. Moving on, how do you program these quantum machines? In this list, we first have Cirq from Google. Cirq is a Python software library designed for quantum circuit creation, manipulation, optimization, and execution. It's optimized for noisy intermediate scale quantum computers where the intricacies of the hardware are crucial to achieving cutting-edge results. Cirq's flexibility and abstractions make it a valuable tool for quantum researchers and developers. Next, we do have Qiskit from IBM. Qiskit is a comprehensive quantum programming framework that empowers users at all levels. It includes an extensive set of quantum gates and pre-built circuits for research and application development. The transpiler feature optimizes Qiskit framework for various quantum processors, supporting custom configurations and third-party plugins. Users can schedule and run quantum programs on local simulators and cloud-based quantum processors with support for different quantum hardware designs. And also, we do have the Quipper language from Dalhousie University. Quipper is an embedded, scalable, functional programming language designed for quantum computing. It offers a wide array of features, including a high-level circuit description language, support for procedural and declarative programming styles, automatic synthesis of reversible quantum circuits, hierarchical circuits, extendable quantum data types, and programmable circuit transformers. It also supports 3 execution phases, allowing circuit generation to be parametric on values which are generated at circuit execution time. Quipper boasts extensive libraries of quantum functions, enabling quantum arithmetic and quantum Fourier transformation, with also efficient QRAM implementation, circuit simulation, decomposition of circuits, and much more. As quantum computing researchers, it's important to address the technical challenges and considerations that underpin the advancement of quantum computing. Now let's explore 3 crucial aspects. Error correction. Quantum computing lies in the inherent fragility of qubits. Quantum states are highly susceptible to noise and environmental interference. Error correction is important in mitigating these issues. Quantum error correcting codes, such as the surface code, are used to protect qubits against decoherence and errors. These codes, much like a fault-tolerant conductor, ensure that the quantum computations are reliable by redundantly encoding information and correcting errors as they arise. Qubit stability. Stability is the backbone of quantum computing. Maintaining qubit coherence and minimizing decoherence are critical. Qubit stability is influenced by factors such as temperature, electromagnetic radiation, and material impurities. Cooling quantum computers to ultra-low temperatures and shielding them from external influences are important. Achieving qubit stability is still a persistent technical challenge that researchers are addressing to realize the full potential of quantum computing. Choosing the right approach is pivotal as well. Quantum computing research spans various approaches from superconducting qubits to trapped ions and topological qubits. Each approach has its strengths and limitations. For instance, superconducting qubits are known for their scalability, while trapped ions excel in qubit coherence. The choice of this approach depends on the specific quantum application, but researchers must navigate these considerations. I believe that open source is the only way to make Quantum Linux a reality because it embodies transparency, allowing the quantum community to scrutinize and validate quantum software, algorithms, and tools. And this transparency builds trust in the quantum ecosystem, assuring users that the technology is reliable and secure. It encourages innovation and creativity by providing a platform for collaboration. Quantum researchers, developers, and enthusiasts worldwide can contribute, share, and build upon each other's work. I believe that it also democratizes quantum computing by making it accessible to a broader audience. It eliminates barriers to entry, ensuring that individuals from diverse backgrounds can participate and contribute. Alright, so in this keynote, I gave you a generic introduction to quantum computing. I also showed you the current trends in 2023 and also explained why quantum computing matters. We also had a chance to look at Quantum Linux, the internal architecture, and how to program these quantum machines. In the end, we also discussed few challenges and why I believe that quantum computing can thrive using open source involvement. Alright, so if you'd like to connect with me, you can Google my name, Pranav Durai, and find me on LinkedIn, GitHub, and Google Scholar. Special thanks to the Linux Foundation for inviting me to deliver this keynote. And even though I wasn't able to physically meet you all in Monterey, I feel this was able to take me closer. Cool. Thank you for listening to me. Live long and prosper.